everybody. In this video, I'm going to explain about the basis of the two-phase PSV calculation based on the homogeneous equilibrium method explained in the API 520 standard part 1 Annex C. I'm going to explain what is a two-phase PSV and how we can derive the energy balance for isentropic process, and also about homogeneous equilibrium method for two-phase PSV. Two-phase PSV is a two-phase or single phase that flashes across the PSV. One of the examples for such a PSV is a liquid-filled vessels. For example, there was a H2S extractor where MEA was used to extract H2S from a mixed stream of C3 and C4 in a saturated light end unit in the refinery, and a two-phase PSV calculation was applicable. To determine the mass flux through a nozzle of a PSV, the nozzle is assumed to be adiabatic and reversible, which is isentropic. And series of isentropic flashes of the relieving fluid needs to be done, starting from the PSV inlet conditions. Here, I explain how we can derive the formula for calculating flux for the isentropic process. Energy balance for isentropic flow. The general energy balance is delta H plus 1 over 2 U to the power 2 plus Zg times M equals Q dot plus W dot. And in this formula, U is velocity and the whole term on the left side is the internal energy. du is TdS minus PdV. H is U plus PV, so dH is du plus PdV plus VdP. dH is TdS, instead of du we put TdS minus PdV, so PdV cancels each other, so dH equals TdS plus VdP. For a reversible process, ds is 0 because entropy is constant. Therefore, dH equals VdP. Now, equation 1 will be dH plus d1 over 2 u to the power 2 plus dzg equals 0 because there is no work, so W is 0 and it's an adiabatic process, so Q dot is also 0. From 2, instead of dH, we can put VdP. So VdP plus U du, because d of 1 over 2 u to the power 2 is u du equals 0. And if we do the integration, u du is equals VdP. So integral of u du is u2 to the power 2 minus u2 to the power 1, u1 to the power 2 equals minus 2 times VdP. G to the power 2 is minus 2 integral of VdP divided by V. And G is kilogram per second times a square meter. V is cubic meter divided by kilogram, specific density. Or G2 times V equals U. So each of these formats can be used. And this is flux. So flux is the square root of minus 2 times V times dP divided by V. This is the formula that we can use in the homogeneous equilibrium method to calculate flux. And in order to get the integral, we use the numerical method. The integral can be readily evaluated numerically by direct summation over small pressure intervals. This is the midpoint integration rule. Integral of Vp times dP equals delta P times V of P1 star plus V of P2 star, etc. V of P1 star is the volume, a specific volume at the pressure, at the average pressure between P0 and P1. The two methods that can be used to get the mass densities and hence specific volumes are expander block with polytropic efficiency set to 100%, or creating property table for getting the combined phase density values at different pressures. These two methods are explained in a separate video in HYSYS. At the end, I'd like to add some other information. In addition to sizing the PSV, we also need to size the inlet and outlet pipe. Total inlet frictional pressure drop between a vessel and the inlet of the PRV should be less than 3% of the set pressure in gauge. Allowable built-up back pressure, both frictional and kinetic, should be 10% or 21% of the set pressure for fire. The contingency that sets the PRV size is not necessarily that which results in the maximum built-up back pressure. Rated capacity should be used except cases involving either fire or 100% liquid. And the reference is API 520 Part 1. Also, it's good to mention that Aspen HYSYS version 8.3 and after has a module for doing the PSV calculation, so it may be worth to check that feature. This concludes my presentation.